Therefore, carbon dioxide can't be further oxidized. Therefore, carbon dioxide can't convert dichromate to Cr3 plus I. So that can't be a carbon dioxide or carbonate ion. Because of colorless gas, it can't be a nitrogen dioxide either. So it may be sulfur dioxide or H2S. Both can change the color of dichromate to Cr3 plus. Among them, you need to take the gas as sulfur dioxide, H2S, because they are talking about formation of yellow-white colloidal precipitate D. Formation of yellow-white colloidal precipitate of D. Yellow-white colloidal precipitate of D. That is a sulfur. So here what happens? Cr2O7 2 minus goes to Cr3 plus and H2S goes to sulfur. This is the reaction. So appearance of sulfur in this kind of situation is initially white colloidal suspension. White colloidal suspension or colloidal solution. Then it turns to yellow. Here the formation of milk of sulfur takes place. Then finally it will be turned into the most stable allotropic form of sulfur, that is rhombic sulfur. Rhombic sulfur is the most stable allotropic form of sulfur. So any form of sulfur eventually converted to the rhombic sulfur, yes, that is yellow in color. So it is okay. Now the anion is sulfite, the gas is, anion is sulfite. You have anion sulfite to produce H2S. So the gas is H2S, right? So gas E obtained by burning D in air, right? Gas D obtained by burning E in air, burning the gas E obtained by burning D in air. D is sulfur, so that is sulfur dioxide, right? Gas react with gas B. Gas B is H2S. So when you burn sulfur in air, it forms sulfur dioxide. Then the sulfur dioxide react with H2S to produce sulfur precipitate and water. So sulfur gets precipitate here. Again. And colorless liquid F. This is again it gives sulfur. So the colorless liquid is water. Anhydrous copper sulfate turn into blue. It's okay, no? We learned that. When F is added, the white precipitate which forms by reactant C. Right. So what is the solution? Solution is sulfate. Aqueous sulfate solution. Because we add sulfuric acid. So the whatever cation you have in this mixture, in this compound, it will be turned to sulfate. So we know that the anion is sulfide. Okay, anion is sulfide. So now we have to find out what kind of cation included in this compound. So anion is sulfide. It's okay, right? So upon the addition of, here you have sulfate solution. Upon the addition of sodium hydroxide, it produces hydroxide precipitate. We know that all hydroxides are precipitate except one. All hydroxides are precipitates except zinc hydroxide. Except group 1 hydroxide, lithium, expect lithium, and barium, strontium. Except those hydroxide, all the other hydroxides are precipitate. So this will be also precipitate. So this hydroxide dissolves, right? White precipitate. This is white precipitate. Okay. White precipitate. this white precipitate dissolved in both sodium hydroxide and ammonia. So, what is the meaning of white precipitate dissolved in sodium hydroxide? So, this hydroxide corresponding to the amphoteric metal, right? You know, that is a common phenomena for all amphoteric cations. What are the amphoteric hydroxides you have? Aluminium, beryllium, stannous, stannic, chromium, C. These are amphoteric cations. Upon the addition of sodium hydroxide, they will precipitate as relevant hydroxide. Upon the further addition of sodium hydroxide, they will dissolve. You know why? Because Al3 plus OH minus aluminium hydroxide, upon the addition of more hydroxide ions, it turns to aluminate ions or AOH4 1 minus. These are aqueous solution. That's why they dissolve. So upon the addition of H plus, again these observations are reversed. Understand? So this should be amphoteric cation. Right. Now, except chromium, all the other amphoteric cations make white precipitates and dissolve. So you can exclude the chromium because the color of the precipitate is white, right? So except chromium, it can be what? It can be aluminium 3 plus, stannous, stannic, beryllium, C. You can exclude these cations. Why? Because the question says the hydroxide, the white hydroxide dissolves ammonia also. So these hydroxide can't dissolve in ammonia. So the answer is C. The compound is zinc sulfide. It is very good because we know that zinc sulfide is one and only white sulfide that exists in nature. So answer is zinc sulfide. So you can write the answers based on zinc sulfide. Right? Here, listen to this. The A-level syllabus between 2014 and 2019 said that chromium hydroxide dissolved in highly concentrated ammonia to make chromium amine complex, violet in color. But however, regarding the questions that we found recent, we saw that for the most of the questions, they didn't take chromium hydroxide can dissolve in ammonia. For the most of questions that we saw that they didn't take that the chromium hydroxide dissolved in ammonia. It's okay, it's correct. Actually it's correct. Chromium hydroxide only dissolved in highly concentrated ammonia. So when you saw just the dilute ammonia in the question, so take it as like this. So take it. So then if you saw the dilute ammonia, then you can take chromium hydroxide can't dissolve in the dilute ammonia. Right? So only zinc hydroxide can dissolve in the both sodium hydroxide and ammonia. Earlier we knew that both chromium hydroxide and zinc hydroxide dissolves in both sodium hydroxide and ammonia. However, nowadays you need to rememorize that thing like this. Only zinc hydroxide can dissolve in both sodium hydroxide and ammonia. Right? Okay. Now what are the questions based on this question?